Okay. Uh, so today, I just want to start with an outline of where we're headed, because I think we have about 3 more talks left, and then we'll give it to Michael, and he'll talk about Lie theory applied to phi. So here are some topics that I want to talk about, and they kind of follow in order, at least based on what we've done before, logically, so that we could go in this order, but we might also jump around, and we might go in some more depth or less depth on each of these topics. There's no way I could really go into any great depth in the remaining ones.
Oh.
So the first topic is actions in orbits of the Lorentz group, and this is sort of the punchline of the last 2 talks, so I want to mention that at least. In that way you can have these 2 big words under your belt, and I think I want to give you a really gut feeling of what orbits and actions mean, and what they, geometrically, what you should think of, why we care about these things. The unitary group, I want to at least mention it, because we are sort of geared toward applying this stuff to physics, and this is one of the biggest applications. The Lorentz group is a big application, and the representations of the Lorentz group in particular. But the unitary group is too, because that is basically the symmetry group of quantum mechanics, you could kind of say. So it's a way of operating on the Hilbert space and preserving all the probabilities. So Hilbert space is going to have that symmetry. And then to finish a proper discussion on a seminar on Lie groups and Lie algebras, the relationship between these 2 objects should be discussed. I haven't talked a whole lot about Lie algebras actually, and that's because I haven't had this object, the exponential of a matrix. And as soon as I have the exponential of a matrix, this allows me to get from Lie algebras to Lie groups. Okay, so and it's basically just the exponential relation. You take the exponential of a Lie algebra element, you get a Lie group element. But what does all that mean? So we can talk about that in more or less detail. And then representations, and this is, for physicists especially, this is the punchline of Lie groups and Lie algebras. We care about their representations. Representations provide basically actions. So the representations allow us to act with these group symmetries on vector spaces or on general manifolds. All right. So I'm going to erase these. Did you guys do them down? These were just the generators of the special orthogonal group in 3 dimensions. And actually, I'm not going to erase them because I want to juxtapose these with a different set of matrices. And I'm going to come far right to leave this. Okay. So this I'm going to give in the form of an exercise. And these are pretty routine calculations, although they did require some knowledge of the hyperbolic functions. So let me just write the exercise down. This is hyperbolic hyperbolic cosine of eta, cosh eta, sinh eta, sinh theta, cosh, theta is in SO1, 1. This is the generalized orthogonal group we've been talking about. It preserves that generalized metric. And it also has, the S means it has determinant 1. Real quick, did I give a closed form? In the same way that I gave SO3, I'm not sure I gave you a closed form sort of mathematical encoding of. I told you what the generalized orthogonal group meant geometrically. It preserves, so this would preserve O11 would preserve this metric. Basically, it's going to be G of X, Y equals X1, Y1 minus X2, Y2. And really these, if I correct my indices, should be down. Okay. So that would be my norm, and that, yeah, that's right, because I had my minus signs come in last. And if this was 1, 3, then you'd get the normal Minkowski space metrics. You'd have 3 of these guys with the minus sign. Okay, so real quick, let me mention a closed form for this. O of n k is all the matrices A that are n plus k by n plus k, such that A transpose G A equals G. Okay. Where this G is the matrix then. So G is going to be this matrix of plus ones right there, and then minus ones on the last. So I did nk, so this is going to be an n by n up left, and this is going to be a k by k, and everything else is 0. It's just a diagonal matrix. So you have n plus 1s, k minus 1s. So that's your matrix G. So anything, this is the closed form of nk. And then you can say that, let's do this in a sort of short manner. There's a homomorphism called determinant from O and K into the reals. It's just the determinant of the matrix. You can, we talked about the determinant before, and it preserves products, and you can show that it's in fact a homomorphism, so this is kind of a claim that should be shown. Then the kernel of the determinant is subgroup O and K. It's actually a normal subgroup, right? The kernel of any homomorphism is always a normal subgroup. Kernel, by the way.
Yeah, back up a little bit. It's been a while since I saw that word.
In the kernel, so kernel, this is for any homomorphism phi. Kernel of phi is the set of all G, and so for any, I'll write like this, for any phi from G to H, it's a homomorphism. The kernel of phi is all the elements of G such that phi takes G to the identity in H. So I'll write it like 1 H. Alright, so you've got G over here, you've got H over here, and there's some phi goes from there. So there's an identity over here, 1 sub H, and I look at, okay, everything that went to that is something over here. All these guys got mapped to the 1. This is my kernel.
Okay.
And so, for example, a linear map is a linear isomorphism. That means it has an inverse. It's invertible if and only if the kernel of that linear map is trivial. It has 1 element. That means that.
Wait. Say that. What you just said. Say that one more time.
Okay. This is sort of where you might have seen it before.
Okay.
A is invertible. If and only if the null space today, it's the same thing. I'll just write it like this. Kernel of A is just the 0 vector. Okay.
Okay.
Okay, so A is a linear transformation from some vector space to some vector space.
Right.
And you can look at